A 70 billion parameter model needs 141 gig of VRAM just to load. Your 24 gig GPU isn't close. Quantization gets it to 42 gig, and I'll show you exactly how. Full precision Llama 3.170B is 70.6 billion parameters at 2 bytes each. That's 141 gig of weights alone. Quantized to Q4KM, the real Bartowski GGUF file is 42.52 gig. A 70B model does not meaningfully fit on one 24 gig card at any quality worth using. Only the 2D-bit IQ2 XXS quant at 19.1 gig squeezes on, and Bartowski's label calls it very low quality. IQ1EM at 16.75 gig is worse and not recommended at all. The honest target is 48 gig of VRAM, one bigger card or two, split with tensor split. Running the whole pipeline live at 70. B-scale isn't realistic. Downloading the 141 gig checkpoint and writing another 141 gig F16 intermediate file needs over 300 gig of free disk before you type a single quantize command. So I'm demoing on Llama 3.18B instruct instead. Same exact commands, just a 16 gig F16 file instead of 141 gig. The quantize step itself only takes minutes. It's the download and conversion that eat your afternoon. The naive size formula holds too. Params in billions times, bits over 8. Q at key 0 for this 8B model lands at 8.54 gig, right where that math predicts. Installing llama.cpp today is one line. Homebrew, Wing It, Nix, or Conda Forge, and the Conda build ships CUDA, Vulkan, and Metal backends already compiled in. Building from source with CUDA support is just as short. Clone the repo, then CMake with ggml CUDA on, then build with 8 threads. 2 tool names matter, and both changed. The converter is convert.sh to GGUF.pi. The old convert.psi is gone, and the quantizer binary is llama-quantize, not the old bear-quantize command. First, pull the model down with the HF CLI. The old Hugging Face, CLI download command still works the same way. Then convert the checkpoint to a full precision GGUEFF. The script takes the model folder, an outtype flag, and an outfile name. Outtype accepts F32, F16, BF16, or even Q80 directly, but F16 is the right choice when you're about to quantize again afterward. That F16 file for the 8B stand-in lands at 16 gig. For the real 70B, it would be roughly 141 gig, which is exactly why nobody demos that part live. Here's the actual trick. A K-quant doesn't quantize every weight alone. It groups weights into blocks and shares one scale across the block. Q4K packs 32 weight blocks under one shared scale, landing at 4.5 bits per weight. Q5K uses that same 32 weight layout at 5.5 bits. Q2K and Q3K both use smaller 16 weight blocks at 2,625 and 3,4375 bits. Q6K also uses 16 weight blocks, but with 8-bit scales, landing at 6,5625 bits. That shared scale is what lets each weight get away with so few bits. The expensive full precision number gets paid once per block, not once per weight. There's one exception. Q2K still keeps the attention output and the feed-forward down projection at 4 bits instead of 2, because the original PR found perplexity spiking to 9.0 on a 7B model when those specific tensors got pushed all the way to 2-bit. Beyond these, llama.cpp also ships ternary quants, TQ10 and TQ20, at roughly 1.7 and 2.6 bits per weight, the newest addition beyond the original K-quant set. Now the actual quantize step. Point llama-quantize at the F16 file, name the output, and pick a type. Q4KM is the one every source agrees on. Good quality, the default size for most use cases. On the 8B stand-in, the 16 gig F16 input becomes a 4.92 gig Q4KM file, roughly a 3x shrink, for a real cost of +0. 0.1754 perplexity on Llama 3 8B versus F16. Run it again at Q5KM, and you get 5.33 gig for only +0. 0.569 perplexity, barely worse than F16 at all. Put these numbers on a chart and the story is obvious. Against a 5.9066 F16 baseline on a 7B model, Q2K comes in at 6.7764, a real, audible quality drop. By the way, I post one of these every day. Subscribe if local AI is your thing. Q3KS is 6.4571. Q4KS drops to 6.215 plus 0.11. Q5KS is 5.9419. Q6K is 5.9110, basically free at plus 0.7. Every source, the original K-quants PR and llama-quantize's own current numbers, agrees the honest floor sits around Q3K, or roughly 3.5 bits per weight. Below that, you're trading real output quality for disk space, not getting a rounding error. K-quants use one linear scale per block, simple and fast. I-quants, the IQ prefix types, map weights onto a non-linear codebook instead, pre-computed value grids rather than a single scale. That lets them pack more usable precision at very low bit counts, the 1 to 3 bit range, at the cost of running slower on some backends. IQ4XS sits at 4.25 bits per weight, IQ4NL at 4.50, both non-linear. There's no universal ranking across every model, but I-quants specifically pull ahead in that very low bit territory where linear K-quants start falling apart. An importance matrix changes what the quantizer protects. Run the unquantized model over calibration text. Record which weights actually move the output. That's your matrix. The quantizer steers rounding error away from the weights that matter most instead of every weight in a block. The effect is biggest at low bit counts, so virtually every serious Q4K and below GEGUF ships with one now, Bartowski's own repos, are literally labeled llama-imatrix quantizations. Generating one is a single command. Point llama-imatrix at the F16 file, give it a calibration file, name the output, and offload 99 layers to GPU so it runs fast. Bartowski uses a file called calibration datav3.txt for his own release quants, a higher entropy general corpus, not plain wiki text, that's community consensus, not an official spec. Feed that imatrix straight into llama-quantize with the i-matrix flag and pick a low bit type, IQ4, XS, here. That's the step that actually earns the low bit quant its keep, a real quality gain, right where linear K-quants would otherwise fall apart. And even without an i-matrix, K-quants already beat the legacy Q40 line at the same file size. That's why Q40 isn't recommended for new quantizing anymore. Here's what actually fits and how fast. A 24 gig card only gets IQ2 XXXS at 19.1 gig, Bartowski's own very low quality label. A 48 gig card holds Q4KM at 42.52 gig with about 16K tokens of headroom, though Q5KIM's 49.95 gig sits right at that same card's edge. The 8B demo's Q4KM file, 4.92 gig, fits almost any GPU. One third-party RTX 4090 benchmark got 18 tokens per second at 40 of 80 layers offloaded, and 8 tokens per second at just 20 layers. And KV cache scales separately. At Llama 3.170B's full 131K token context, it runs about 40 gig alone before a single weight is counted. A few real failures worth knowing. Converting a brand new architecture too early fails with exactly model Ministral 3 for causal LM is not supported, fixed by updating transformers and llama.cpp's own master branch. A model shipping only tokenizer.json instead of the legacy tokenizer. Model errors with missing tokenizer model, a real gotcha on modern Gemma and Quen releases. An out-of-memory failure like insufficient memory attempted to allocate 491,520.0 MB often traces back to a misconfigured context size. Check your flags before blaming your RAM. And some Q40 quants of 70B models have output pure gibberish, while Q4KM and Q50 builds of the same source worked fine. Always sanity check a fresh quant's output. Last thing, should you even quantize it yourself? Pre-quantized GGUFs for popular releases show up on Hugging Face fast, and the GGUF my repo space runs the whole pipeline server side, no GPU required. The real reason's to still do it yourself. It's your own fine-tune nobody else has quantized. You want an i-matrix built from your own domain data, or you want a brand new quant type the day it lands, before anyone else has requantized it. Q4KM is the real default the evidence backs. Good quality, huge size cut. A 70B model needs about 48 gig of VRAM to run well, not the 24 gig a thumbnail might imply. Someone's probably already quantized the model you want. Learn this pipeline anyway. You'll need it the day you fine-tune your own.